Everyone, my name is Abigail Shannon, and today I'll be talking about Euclid's Elements, Book 1. More specifically, Proposition 15, which states if two straight lines cut one another, they make vertical angles equal to one another. So what he is saying is this angle and this angle are equal to each other, and then these two angles are also equal to one another. When it comes to our proof, when I first read through this book, I was so confused and it seemed really overwhelming. But I realized once I sat down with a blank piece of paper and just started following these proofs, which are essentially instructions, it made it so much more clear to me on a majority of these propositions. So that's what we're going to do today, or I'm going to try my best anyway. So to begin the proof, he says, for let the straight lines AB and CD cut one another at the point E. So that means we need a straight line AB, which will be here. I apologize for the handwriting and the line work here. I'm trying to draw with my mouse, and I'm not great at it. So the straight lines AB and CD to cut one another at point E. So now we need our line CD. Now, the awesome thing about this proof is CD does not have to cut right here on this line. It could be here or here. It does not matter. That is the glory of this. Anywhere the two angles adjacent will be the same, or across from will be the same, sorry. So his proof is essentially saying that A, E, D, and C, E, B are the same. Now I need to put our intersection here, which is, oh my lord, that is crazy. You didn't see that. Our thing here, our point here, is E. So angles AED and CEB are the same, and that would also mean, by his proof, that these two angles are also the same. So, to make this easier, when I did it, I numbered the angles. So AED would be angle 1, AEC would be 2, CEB would be 3, and then obviously DEB would be 4. That just makes it a lot easier for me instead of saying AED, AED, DEB. So my steps are by numbers, but you can look at this picture to understand a little bit more of what I'm saying. Let me just delete all these little drawings so it's a little bit easier to see. So the next step here, which is where we begin our proof, is that angle 1 and angle 2 are equal to two right angles. So our first angle would be angle 1, and angle 2 are equal to two right angles. So if we draw this out on its own, it would look a lot like this, right? This is angle 1 and angle 2. That's right here. And so what this is saying is angle 1 and angle 2 are equal to two right angles. And we know this to be true. It's because earlier, two propositions before, it states in Prop 13 that if a straight line set up on a straight line makes angles, it will either make two right angles or angles equal to two right angles. So a straight line set up on a straight line is equal to two right angles. We know that to be true. That also means angle 2 and 3 are also two right angles, because angles 2 and 3 look like this, which is exactly what we just saw with angles 1 and 2. And it's by the same proposition, same Prop 13, which states if a straight line set up on a straight line makes angles, it will make two angles equal to two right angles. So that is true for all angles on this proposition. Going forward now, we know, because of common notion number 1, which states things that are equal to the same thing are also equal to one another, which means angle 1 and angle 2 are also equal to angle 2 and angle 3 because they are both equal to two right angles, or as we know, a line. Next, Euclid says what we shall do is subtract our second angle from both, because as we see on our equation, there are two of the same things. That means we could subtract two of the same things, and then we get our solution, which is angle 1 here, and angle 3 must be equal to one another because of our common notion number 3, which states if equals be subtracted from equals, then the remainders are equal. So our equals here are angles 2, subtracted from angle 2. That means the remainder, which is angles 1 and 3, which is AED and CEB, must be equal to one another. So this is our proof for angles 1 and 3. The same can be done for 2 and 4, but for the time, this is what I'm going to prove today. Some examples of this in real life are things like a pair of scissors. Obviously, with the way scissors are made now, the shears themselves can kind of be bent at the handles. But if you get a straight shear like this, we can see, you know, if we follow this angle all the way up the shear, it would be this angle and this angle, the same. We see this also on folding chairs. It's this interior angle here, as well as these being the same. So we do see this commonly in the real world, which is so cool. So thank you guys for listening to my presentation, and I hope that helped a little bit.